Hello and welcome to York University Astronomy and Astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. You will now find us wherever podcasts are distributed. I'm Paul Mackin, one of your hosts this evening, and I'm joined by Professor Mary Helen Armour. We are broadcasting live from the Allan Carswell Observatory, located at Keele campus of York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday at 9 p.m. local Toronto time, or currently 1 a.m. Tuesday Universal Time at York U Observatory. We also run in concert with our online public viewing, or as we call it, the OPV feed, run by the observatory staff, uh, who I am told are doing live observing with our 1 meter tonight. To navigate to our live show or find out more about us, please check out our website at yorku.ca/science/observatory and follow the link to our online public viewing chat on YouTube. Any questions or comments you may have on past shows or suggestions for future topics, please send us an email at observe@yorku.ca. We can also connect with us on Instagram with the handle at Yorku Observatory, or on Facebook at Allan I Carswell Ob. All of our programs are free, but if you feel like you'd like to make a donation, and we'd certainly appreciate that, please see our website at yorku.ca/science/observatory. We'll be monitoring the YouTube chat for questions and post content. Tonight's weather isn't looking too bad for observing, and as I said, the team is going to be using the 1 meter. We have the domes open, and we'll likely be mixing live images with some archival images on the OPV. How about you, Professor Armour? How are the skies up where you are?
Cloudy. I live north. I'm a fair bit north of Toronto, and it's reached lake effect snow season, so it's rather unpredictable. And I'm just hoping it doesn't snow tonight.
Yeah, it's funny because if you actually look on a map, you take the observatory, you take where I live, and you take where you live. I'm kind of halfway in between. So I've got partly cloudy skies, no real sign of snow, although there's a fair bit on the ground right now. It's funny because I was on campus today and not a sign of snow in Toronto. Up here, fair bit, and up where you are, I think there's even more. But welcome to winter in Canada. And once you get away from Toronto and the lake effect down there, it starts to get a bit messier. But speaking of cloudy skies, unfortunately tonight's cloudy for you, and you've got great skies up there normally. But there's a big event going on, and I think we're going to be talking a bit about that tonight. But maybe we'll start the show this evening with some space history. So, how about it, Mary Helen? Why don't you tell us about it?
Well, if you follow sort of pattern, sort of the regular cycle, tonight is actually the peak of the Leonid meteor shower. Whether you will see it or not depends a lot on the weather where you are. So the Leonid meteor shower has a long and fascinating history, and I'm going to come back to it a couple of times throughout this. But it's associated with the comet 55P Tempel-Tuttle, and it has about a 33-year orbit. Now, what is really interesting is this has produced some of the most spectacular recorded meteor showers. They actually become meteor storms. They get to be so intense. So the first really well recorded one of this nature was in 1833. And there are woodcuts and artwork of these things, and it literally looks like it is raining meteorites. They estimate for the 1833 shower, there were counts of up to 240,000 meteor sightings in about a 9-hour period. So you are talking thousands of meteorites a second. It literally looks like the sky is raining sort of meteors. It's just absolutely spectacular. So that was 1833. And then in 1866 and then 1867, the sort of subsequent year, they also had very spectacular showers, not quite to the extent of 1833, but still quite intense showers that were recorded in both sort of North America and Europe. And again, this was sort of one of those fascinating phenomena because this is really, of course, in that same time when we've discovered new planets in our solar system, of course, like Neptune and Uranus. You've discovered the minor planets. And so they're starting to think in terms of like there's a lot more stuff out there. And what the Leonid meteor showers, from a historical viewpoint, really triggered was this look at some of these very small bodies and could they actually hit Earth? So what the Leonid meteor shower did was really start astronomers thinking about the possibility of these rocks actually hitting Earth. Now, it had kind of been assumed prior to this that it just wasn't possible for rocks to fall to this from the sky. And this goes all the way back to Aristotle and some of his ideas. And he sort of thought some of these, meteors that actually, the meteorites that actually hit the ground were from volcanic eruptions. With these intense showers, people started to think a little bit differently. Um, and even at that time, there was really resistance to this idea of rocks hitting the ground. I think it was one of Andrew Jackson who said, I would rather believe that two Yankee scientists would lie than rocks can actually fall out of the sky, or, something roughly to that extent. I could be misquote. I could have the wrong person, but the idea was these very public figures were saying, no, 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 this just isn't, it isn't possible. This isn't how the universe works. And yet the Leonid meteor showers really started scientists thinking about if these are sort of streaking through Earth's atmosphere, is anything actually landing on the ground? And this is really sort of this start of this hunt for meteors, and later then sort of leading into sort of understanding that it is possible even to create larger things like impact craters. And of course, the Barringer meteor crater in Arizona is very famous for, finally being recognized as an impact structure. So this whole idea, sort of this branch of astronomy and this sort of study of sort of meteorites hitting the ground, and later impact craters really stems early on from these Leonid meteor showers and these very spectacular 1933 and 1966 showers. So 33 years apart, these two, so they go, okay, this happens every 33 years. They started looking for it in 1899 and it kind of fizzled. It didn't happen. Like there was still a shower, but you didn't get the spectacular light show that you did in sort of 1866 and 1833. So it started to kind of fade out of the consciousness, but these really spectacular showers were a real sort of catalyst and trigger and sort of an important stepping stone to really starting people looking at meteorites and eventually impact craters and sort of understanding that yes, there are actually rocks on Earth that have come from outer space. Right? So it was, although we think of it, oh, it's a pretty meteor shower, if you put it in sort of this historical context, it really is quite interesting to see how this sort of all fits together. And actually, the comet was discovered sometime after the two showers, and the two were later linked together in the 20th century. So
It's funny because when I go and observing in the summer, I do, and this is something we'll probably talk about at some point in the future. I do a little bit of pop-up astronomy where you set up a telescope somewhere dark and basically people look through it. But one of the questions I often get about, is about meteor showers. And I point out to people that if in your average dark sky night, if you've got a dark, clear sky, you can see 7 or so meteors an hour. But when a meteor shower happens, even an anemic one, the number goes up dramatically. And it is really kind of breathtaking to see it. And I've never seen a meteor shower, I don't think any of us have, of this level. But I have seen, meteor showers, not meteor storms. And they're stunning. It's really just incredible to
Yeah.
experience. And
And
unfortunately, I think tonight it's a short one, but I think we'll be talking more about that a little later.
yeah,
So
and it's like I said, the Leonids are famous for producing these kind of storms, and I'll talk a little bit more about some of the more modern ones and as we go along.
yeah,
But it's fascinating, when you think about it, if you think about it, we have been observing these sort of meteor showers for a very long time. But it's only in sort of the last, maybe 100 years or so that we really put together all the pieces of where these things come from. In some ways, we knew more about stars than we knew about meteorites. If you go back to like the late 1800s, early 20th century, we knew more about stars than we knew about meteorites, and we knew about meteor showers, which, if you think about it in a way, is quite the thing, right? But because they are so, I don't know, I don't think ephemeral is the right word, but they're just shooting stars, and nobody thought about them until you get an event like the Leonids that produces this kind of spectacular event. But it was interesting because in 1899, when it didn't really happen, sort of, you didn't get this kind of storm again. It seemed to have just, fizzled out. They thought, oh, okay, it's over. It's not coming back again. Whatever it was, it was sort of a one-off kind of thing. And it's like I said, and then you don't see it again for a number of years, and we'll sort of get to a little bit more of that later. But it's like I said,
yeah,
we forget, like, meteor showers happen all the time.
they do.
If you look at a calendar, there's probably always one happening. They peak. I mean, this is the other thing you have to remember. They peak on a certain night, but you can usually see uh, meteors from the shower within, at least a week or two on either side. Like the Perseids are probably the most famous ones. They peak in sort of, early to mid-August. But the truth of the matter is you can see them for at least a couple of weeks before and a couple of weeks after fairly consistently. I mean, the Perseids are probably the most consistent shower we have. And one of the easiest ones to see. And at that time of year, you usually have more clear skies. So more people are familiar with that one. But if you really look at it, the Leonids, when they're at sort of their peak, just way outshine any of the other showers.
Yeah, it's interesting. You mentioned if you look at a calendar, if you look at an astronomy calendar, generally they'll show you when you have peak periods for meteor showers. And of course, this is my chance to plug the soon upcoming 2026 AICO calendar, which does list those events. So we'll be talking more about that over the next couple of weeks, I think. But let's move on to another item in astronomy history. On November 16th, 1974, there's a lot of famous astronomers, but I reserve the title legendary for very few. Frank Drake is definitely one of them. So under his guidance, uh, a group gathered at the Arecibo Observatory in Puerto Rico, and we talked about this a couple of weeks ago, actually. And there was an upgrade to the facility, and they had a big reopening ceremony. And after the requisite speeches, scientists used the radio telescope to send what would be known as the Arecibo message. It was 1,679 bits of data in 73 lines, each 23 characters long. It sounded, to the assembled crowd like a two-tone little song about 2 or 3 minutes long, but encoded in the codes was a message crafted by a team of scientists led by Frank Drake, and the team included Carl Sagan, which showed a rough picture of a human, a rough structure of a DNA double helix, and a map of Earth's position relative to in the solar system. The information was aimed at M13, which is a globular cluster about 25,000 light years away in the constellation of Hercules. And since it takes thousands of years for the signal to get there, not to mention the time any signal sent back by extraterrestrials who interpreted it, you know, it wasn't so much a message as a demonstration of how we might do it. Now, Frank Drake is a really interesting character, and among what I feel uh, are his greatest accomplishments, or his single greatest accomplishment, is his attempt at modeling the probability of attempting to find intelligent life in our galaxy. He came with an equation, and one of these days, I'm going to talk my wife into letting me add this to my science tattoos. But the Frank Drake equation is used to estimate the number of active communicative extraterrestrial civilizations in the galaxy. And the way it works is that you take the number of stars in the galaxy, and then you kind of try and estimate the fraction of the stars with habitable planets. And then you try to estimate of those habitable planets, what's the fraction of them with life? And then you say, of those with life, what's the fraction of them that have intelligent life, intelligent civilizations? And then you ask a couple of interesting questions. You say, well, how long will an intelligent civilization exist? The eventual outcome for every species that we know of is extinction. So, I mean, eventually humans will go extinct, and so will all animals and life on the planet on this planet. So, how long does a civilization last? And then, how long is does a star last? And that's a really interesting question in itself, because some stars are very short and some have very short lifespan, a couple of million years, and some can last upwards of a trillion years. So you model this out in this equation, and given the number of stars in the Milky Way, which are estimated between 100 billion and 400 billion, and the fact that we see planets almost everywhere we look with stars, we've currently got about six, or as of October 30th, 6,128 known exoplanets and another 8,000 or so possible candidates. The numbers start to look promising. Now, we don't know the fraction of the planets that are habitable, and we actually don't even know what habitable means. Habitable might mean one thing to us, but you can have life forms that would find our planet, you know, uninhabitable. And, we might have planets they find perfectly habitable. So there's some complexities here, but the numbers start to look promising. Um, so, but we are speculating here but it seems likely based on the vast number of stars in the galaxy and the percentage with planets. And again, we can assume that some are habitable, that there is intelligent life out there somewhere. Then we run into another problem. Can we communicate with them? Do they even use radio? We're not using radio as much as we used to. We use close, fiber optic communications and other things. So, there are real complexities to this that aren't covered. But Drake's equation, is the first attempt to actually quantify this. And to me, that's entirely fascinating.
Yeah, I mean, and I don't even know so much if he's trying to. I'm not sure quantify it is even a great term for it, but it's trying to think about what are the factors we have to consider, because a lot of these we can't even put numbers to even now, right? They're
Correct. Yes.
estimates, they're guesstimates. But what I think this equation really does is it focuses on what are we looking at? What can we talk about in the way of probabilities, right? Like what things do we have to take into account? And then we can do sort of best case and worst case scenarios. And I remember Carl Sagan doing this on the Cosmos series. He went through it and he had everything from like, I think the lowest number was like about a 2 up to tens of thousands, right? Depending on the kind of numbers you put in. Now things like number of stars, number of planets, we're getting a much better handle on that kind of thing. Um, but it's like you said, even how do you define a habitable planet? Earth is obviously habitable. Venus and Mars in our solar system are kind of on the edge of the habitable zone. But then you get something like Europa or Enceladus, where you might not find intelligent life, but you certainly have the potential for finding life. So in some ways, like some things we can resolve. In some ways, it's gotten more complex. And some people I've heard talking about, like, do we need to update the Drake equation? Because there are factors we know about now that we didn't at the time that he was living, or working on this. So
I
I
think
think
he's
what it
still
really does
alive.
say,
Yeah.
is he? Okay, it's like I said, I thought I saw something not that long ago, but the thing is, in the end, what it really does is it focuses us on, like, what are the things that have to go into potentially finding extraterrestrial life? What are the things we have to um consider? So it's like I said, I don't even think of it so much in a numerical way. It's kind of a Fermi problem, right? There really isn't a right or wrong number. Um, but it makes you start to think about what factors do we have to consider. So
Yeah, it is. And just to confirm, I just quickly looked it up. He died just over 3 years ago at the age of 92.
yeah, it's like I
But
said, I remember, I thought I remembered seeing something about his death a year or two back. So yeah.
yeah, but I mean, again, you're correct. This is not an attempt to estimate so much as perhaps propose some way of looking at it, or some approach towards modeling. But there are so many variables. We don't really know, but it causes us to ask the right questions, I think.
Yeah.
And the questions are getting more complicated. Um, I just want to take a slight detour here and just point out that if you take a look at the OPV feed right now, I believe we are imaging, it looks like Saturn. It's kind of overexposed, and Saturn's moon Titan. I think that's what we're looking at, but please keep an eye on that. Mary Helen, I'll turn this back over to you for more of our Leonid
Yeah.
friends.
So it's like I said, I'm fascinated by the Leonid meteor shower because, of course, my area of research involves impact craters. So this whole sort of idea of meteorites and meteors and impact craters and all that kind of things hitting Earth kind of fascinates me. And so the interesting thing about the Leonid showers, of course, in 1899, then it didn't happen. And people kind of forgot about it. Like it was kind of one that was still there, like we'd still get some meteorites. But then in 1966, the comet passed again close. And the thing about the Tempel-Tuttle comet is it's a relatively small comet. It doesn't generate that big a tail. So sometimes when it passes close to Earth, it can leave the huge sort of a very good dump of stuff for us to go through. So you get these very spectacular meteor showers. And other years, its orbit gets disturbed, and because its tail is relatively small, you don't get the same amount of meteors, right? So in 1966, it came back and it produced another very notable shower. Not an 1833 kind of shower, but certainly something that was, quite, like up there for like, okay, this is way more than we normally see kind of thing. And it was sort of in this time frame too. They found the Tempel-Tuttle comet. They realized the sort of link between the two of them. By this point, they had sort of linked other showers, I think, to other comets. You were getting to the point where, observing was good enough that you could do this. But in 1966, here comes this comet again. And so at this point, they started thinking in terms of, okay, we're going to do sort of a Halley's Comet thing, and we're going to look back through the historical records and see if we can see other examples of these showers. And sure enough, they were there. They have tracked it all the way back to some records as early as around 900 AD. So these records of showers were there. It's just until you kind of understand that there's something periodic. Uh, you can't put it together. And with the Tempel-Tuttle and the Leonid meteor showers, it was more complicated because you don't get the same kind of spectacular peak every 33 years, which would have made it obvious long before 1833. It's because this comet's orbit gets disturbed and it's relatively small, it doesn't always produce these really massive showers. Sometimes it does, and often it doesn't. Right? But so in 1966, this started sort of people tracking back and sort of finding this shower in about records of the shower back to about 900 AD. 1966. Okay, 33 years from then, what's going to happen next? So what we ended up having is in 1999, 2000, and 2001, it produced again spectacular showers, particularly in 1999 and 2000. Now, of course, in this part of the world, we're unlucky that the weather is often very bad at this time of year, so it wasn't seen that well in this part of the world. I remember watching 99, 2000, but it was cloudy, just like it is tonight, and never really saw it. But images from other parts of the world, 99 and 2000, showed this absolutely spectacular meteor storm. Maybe not in 1833. That was just sort of something, like exceptional. But certainly you could see it, and they show the images, and they're just like shooting out all over the place. It is just sort of a huge number of shooting stars. Like literally, it's raining meteors. And the one thing to remember too about showers is the reason we name them the way we do is because of the direction in the sky they appear to come from. So, of course, the zodiac is a sort of background of stars that, that are along Earth's ecliptic. So showers will tend to appear to radiate from a particular part of the sky, which is usually associated with with a constellation, often a zodiac constellation, but not always. And in the case of the Leonids, they appear to be coming out of the constellation Leo, okay, which is how they get their name. So if you go out in the night sky, if you want to find the Leonid shower, if you happen to be in somewhere where the weather is a little better than where I am right now, the easiest way to find Leo is to start with the Big Dipper, and you follow the stars from the end of the Big Dipper, which will take you down to the constellation Leo. And it's like I said, it doesn't have to be real precise. You have to be looking just generally in the right area of the sky where the constellation Leo is, and you should see these. But it's like I said, 99 and 2000 and 2001 did produce again up to thousands an hour at its peak. And there are images from various places in the world where it is absolutely spectacular. We live in the wrong part of the world because very frequently at this time of year, the weather does not cooperate. But in other areas with clear skies, the showers, of sort of 99, 2000, 2001 were actually, again, really, really intense. Maybe not 1833 intense, but certainly more spectacular than most of the ones that we do see on a regular basis.
Yeah. When it comes to looking for Leo, the real trick is to identify the big question mark, and then just to its left, there's kind of a right angle triangle, and then you've got Leo. You've got the head of the lion, and you've got the hindquarters of the lion. But and that's a great constellation for looking at galaxies in as well. So it's kind of a perennial favorite. But we've got to move on because we're getting near the halfway point. So I just want to mention one other history item. This one's from a week ago. We missed it, but on November 8th, and that's actually kind of a big deal. On November 8th, 1656, Edmund Halley was born. Now, it's been said that the general public knows three astronomical objects: the moon, the rings of Saturn, and Halley's Comet. So, English astronomer Edmund Halley, born on November 8, 1656, didn't discover the object named for him. In fact, he never saw it. That's the really cool thing. But he made a mathematical prediction of its return. So, what he did was he noticed this comet had been recorded before he was born. And then he found that if he went back in time, a similar comet 76 years earlier, and went back again, and there was record of it. So he predicted that there would be this comet that would come, and it did, and it came after he died. He used he was a friend of Isaac Newton, and he used Newton's theory of gravity to calculate the comet's orbit. And we'll talk more about his other relationship with Newton, but he did a lot of stuff. For example, in 1676, he sailed to the island of Saint Helena in the South Atlantic Ocean, and spent a year measuring stellar positions, the result of which was the first catalog of the southern sky. He was appointed the second astronomer royal, and his discoveries were many, but they include, the period of and the periodicity of Halley's Comet, the fact that it was coming back all the time, um, the proper motion of stars. So he compared stars against historical records, Plotny's second edition, Almagest, and he noticed that fixed stars had actually moved over the centuries. So the stars actually have a proper motion. Uh, he cataloged Southern Hemisphere stars, as I mentioned. He determined the Earth moon distance during his time in St. Helena. He observed a transit of Mercury, where Mercury moves in, sorry, the Earth sun distance, the transit of Mercury, where he noticed the Mercury moved across uh, the surface of the sun, and realized that a similar transit of Venus could be used to precisely determine the distance between the Earth and the sun via parallax. Uh, and he published a call for international cooperation to perform these measurements the next time these transits occurred in the mid 18th century, which led to an accurate calculation. He discovered the globular cluster Omega Centauri, which is, I think, the first, and identified it as a non-stellar object, a star cluster, distinguishing it from individual stars. Um, Other scientific contributions, he helped pay for the publication of Newton's Principia, the Newton's principles of modern philosophy, which is, for early physics, the gospel. Um, he encouraged Newton to write it. He edited the manuscript and personally financed its publication when the Royal Society lacked funds. In meteorology and cartography, he made a lot of sea voyages. He published the first known meteorological charts. And drew diagrams of trade winds and monsoons using symbols which are still used. He worked in geomagnetism. He invented the diving bell. He actually came up with the first actuarial data for life expectancies. And his work became a scientific basis for life insurance business, and that is a major event in the history of demography. He estimated Earth's old age using an ocean salinity method. Uh, so what he looked at was measuring the salinity of the oceans and the rate which salt was carried to them by rivers. His estimate was over 100 million years, which is too low. But it was a revolutionary idea at the time that was used that used a scientific method to challenge the 6,000-year biblical chronology. So he really did a lot of amazing things, and we know him for his comet, a comet that he didn't really discover and never saw, which I think is just a fascinating story.
Paul, that's not true. He did observe it in 1682.
Oh, did he? I
Yes, he
stand
did
corrected.
observe it. He did observe it in 1682, and this is part of what triggered his interest and why he
I
predicted the
stand corrected.
return. But he didn't live until 1758 to see its return, and he was quite let's just say castigated for predicting the return of a comet at a date where he was likely not to have survived to. So he did. There was some criticism of the time that okay, like you're not going to be like a good chance you're not going to survive to see this. You'd be over 100. You'd be getting close to 100 years old, and people generally didn't live that long in that era. But yes, he did
Correct.
observe it in 1682, and he tracked back because, of course, it would have then been there in the early 1600s. So you're talking the era of the Tychos and Keplers and Galileo, and then farther back, right? But
Yeah.
yeah, it was quite interesting, and I think when you look at his accomplishments, the way you have to tie a lot of them together is he was really a mathematician because astronomy was considered a branch of mathematics for the longest time. It wasn't really until into the 1800s where you get into like heavy duty telescope observation that it became more of an observational science, because prior to that it was all mathematics, and that's why Newton's work so revolutionized it, because now you could predict orbits, whether of comets or planets or anything else, much more accurately, right? And that was the point of applying it to Halley's Comet. It was a mathematical problem, right? Not really
Yes.
an observational one. So if you see what ties a lot of his work together, is a lot of it is sort of mathematical in nature, right? Because all of these are sort of
Absolutely.
subsets of mathematics.
Yeah, absolutely. But he was remarkable, and and a contemporary of Newton, and it shows you what a huge burst of scientific knowledge happened around that time. You've got sort of a straight line from Galileo, Kepler, Newton, and Halley, and it's just really remarkable. But on that note, I know we're at halfway point, so a couple of reminders. You are listening to York Universe. We are broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. Please look at our website, yorku.ca/science/observatory, to join the chat. If you have any questions or want to see some of our content, tonight you are listening to Mary Helen Armour and myself, Paul Mackin. We've been discussing historical items, and if you're interested in joining our online public view, please navigate to our website and follow the links to join that fun. And we are observing live right now. I'm not sure what the object is, but there's definitely something on the screen. And I'm guessing it might be Jupiter, but I'm not sure.
Mm.
It's a little overexposed, so we'll see as they start to bring the exposure down and the gain down a bit. We do have a couple of reminders before we get into some news items for the week. Um, we've been doing some maintenance on the observatory in the last little while, but regular observatories tours begin again this week on November 19th. So you can visit our website for free tickets and come and join us. And it really is worth seeing our 1 meter and 60 centimeter telescopes. And 2 weeks from tonight, on December 1st, we'll be doing a holiday show. Rather than our usual format, we'll be looking at holiday ideas for astronomy-minded gift givers. We're hoping that you can join us on the first of what might well become an annual event. We'll see how the response is and how it goes, but I believe it's Mary Helen and I that are hosting it again. So I'm really excited about that, and I'm sure we're going to come up with some great ideas and suggestions. So now on to news. Mary Helen, what about the Leonids this year? What's going on?
Okay. So if you happen to be lucky and are in a location where they can actually be seen, the Leonids are a relatively quiet shower this year. I mean, the last pass of the comet, of course, was in the late 90s. So we've gotten to the point where a great deal of the material has dissipated. So you will still see, like a shower which is comparable to the Perseid. So you're going to get like 10, 20, maybe a little bit more per hour. So still quite a number. And going into the next peak, it will probably be in 2033, 2034. The unfortunate thing is about the next peak is it's not going to be that spectacular. It appears that Templetunnel's orbit has been disturbed by Jupiter. So for at least the next few decades, 2033, 2066, it seems unlikely we will get any more of these spectacular showers that we saw sort of 99, 2000. It'll still be, a good shower, and certainly, still one of the stronger ones. But unfortunately, it's unlikely to be spectacular for the next few decades because of perturbations of the comet's orbit from Jupiter. So it's still a good shower, but it's not going to be the spectacular shower that we have seen, in the past. Because this comet seems to regularly undergo these kinds of disturbances. And because it's a relatively smaller comet, even small disturbances can make a big difference in sort of how much debris gets left sort of on Earth's orbit for us to hit and to produce these meteor showers. So for the next few decades, unfortunately, we are not going to match the sort of showers of 99, 2000, or 1833 or 1866, but it will continue to be a fairly solid meteor shower.
That's amazing. Well, I mean, again, there are many meteor showers in the year. The Perseids in summer are a big deal as well. So pick up your Allan Carswell 2026 calendar, and I promise you, you will find that there are a list of meteor showers you can take a look at. Um, Now, I did want to talk about something in on the space launch space. No, no pun intended. Blue Origin had a second launch of its orbital and reusable New Glenn rocket with a dual spacecraft mission to Mars, and it was successfully able to land on a drone ship. Now, this is a big deal, and it's a big deal in a couple of odd ways. So everyone knows that SpaceX can launch and land a rocket. They've done it with their Starship. They've done it with their Falcon 9. They've done it with their Falcon Heavy, and they've landed components of their Starship architecture. Um, and the Falcon 9 is the most successful launch system of all time. They're up to like 135, 140 launches so far this year with that system alone. It's really quite incredible. But no one else has ever been able to do it, and other companies are trying it now. Blue Origin, uh, so rockets are classified by their lift capability, and Blue Origin was trying to fill a niche. Um, Falcon 9s are smaller rockets, and they can get a satellite into orbit. The Falcon Heavy can get heavier objects into orbit. And then you've got Starship or the Space Launch System, which can lift massive payloads and get them to the moon or the outer solar system, depending on the configuration of the rocket and the payload and whatnot. The New Glenn is designed to fill sort of an intermediate spot, bigger than the Falcon Heavy, not not as big as like something like the Space Launch System or Starship when it finally comes into service. Um, the other thing about it is only SpaceX has successfully landed a rocket. Others are starting to play with it using parachutes or, and helicopters to catch things. Or just there's some plan with the Vulcan Centaur to just return the engines and reuse those. So there's different models, but Blue Origin was able to land the rocket on the second launch. They did this after two tries. And they did one really cool thing, which I loved, because we have lost SpaceX Falcon rockets because they're landing on a drone ship and then waves happen and the rocket tips over and is destroyed. So what New Glenn did, as soon as it landed, the rocket itself welded its feet to the deck to avoid that. And this was actually a mission where they carried a real cargo, and they launched the Escapade spacecraft, blue and gold, two spacecrafts. They were built by Rocket Lab, another private company, and they're smaller spacecraft weighing about 540 kilograms or so, fully fueled, and they are going to Mars. Now, normally, this is not a good year to send a mission to Mars. But we had a window. I think Blue Origin missed it last 2 years ago because they were quite behind. So what they did was they're launching these. They're putting them at a Lagrange point, which is a sort of stable orbit near Earth, relatively close to Earth, and they'll sit there until the proper launch window opens, and then they'll fire their thrusters and head off to Mars. So that's how they're doing it. So the Escapade spacecraft are to study weather on Mars, basically. But this is a very exciting um, uh, uh, mission, because the more options we have to get things into orbit cheaply, And if you can reuse a spacecraft, the price drops down tremendously. The easier it's going to be to get a lot of missions in, and that we'll talk about the return to the moon. We'll talk about missions to the outer planets, unmanned, possible future Mars missions and whatnot. So this really is a bit of a game changer, and it kind of validates the idea of commercial space. The jury's maybe still a little out on that, but it's rapidly falling into place, and private industry is a lot better at launching than government organizations now, because they've had the investment and the time to do it. So they're launching hundreds of missions a year.
The other interesting thing about the Lagrange point, the other thing they were thinking is if you want to catch up sometimes with comets or meteors or some of these visitors that aren't as predictable, if you get another Umea or Atlas from the outside outer solar system, you could, in theory, and this is one thing they're thinking about, is put a bunch of these guys into L Lagrange point orbits and just have them wait until something shows up and then send them out so that you already have sort of the mission in place and it's just waiting for a target to show up. That was the other sort of way they were thinking that, like if this Lagrange point thing makes it to Mars, that this is another possibility for this, where you could have some of them sitting waiting for a target to appear that we really need to look at, because otherwise, it's like I said, if something like Kamehameha comes back, it takes so long to design a mission and get it launched. The thing is long gone by the time you get to it, unless you just happen to
Absolutely,
have
yeah.
something nearby. If you have something already sitting in that L1, all you've got to do is program it to catch up, right? The mission is already ready to go. So they're thinking about potentially doing something like that, I think, with the Lagrange point ones. So that was the other
Yeah,
thing I was
no,
reading about
one
that.
of the tricks with it, of course, is making sure that you've designed a versatile spacecraft with sufficient fuel reserves. But the other option, of course, is to do something like they've done here with small spacecraft, make them as versatile as possible. They're relatively inexpensive, and you put a bunch of them up there, and you've got real options. Yeah, this is a great idea, and I actually think the ESA is looking at doing something very much along these lines, and I think you're going to see sort of a parking lot in an active sense, as opposed to a junkyard parking lot, for the end of life satellites. These would be active satellites waiting for a mission. I think it's a great idea.
And that kind of brings me to my next point. I'm fixated on the meteor shower thing today. Um, we're all quite familiar with the idea of space junk, and I think our last teletube at sort of the end of October uh, was a talk by one of the grad students here at York who's sort of involved in some of these efforts to sort of find and track and figure out what these things are. But that's only on natural objects. What we have to remember as well is natural objects are out there a lot too. And meteor showers do pose a threat. Now, a lot of them are fairly thin, so you don't think about it too much. But the 99 2000 Leonid meteor shower woke them up to the fact that you can have like hundreds of thousands of, pebble to dust grain size things raining down. And the particular threat with the Leonid meteor shower is that these are extremely fast moving. Like everything, like outer space objects are moving, 20 to 30 kilometers per second anyways. With the Leonid meteor showers, they're just over 70 kilometers per second. So not only are there an awful lot of them, they're also one of the faster moving sets of objects. So they have started now to watch for these showers. And if you look from sort of the late 90s, there actually were pictures taken of the Leonid meteorites in outer space, sort of hitting the atmosphere. And we've started to try and catch even sort of regular meteorites and stuff from satellite images. Because as you get more and more satellites, sooner or later, you're going to get one of these meteor showers where, a pebble-sized object, and if it's coming in at the speeds these things can move, you could like destroy a satellite very quickly. And the more objects we have up there, we worry about space junk, but the other thing they're starting to consider is if you have these meteor storms, if you had something the magnitude of 1833 happen now, it could wreak some major havoc on some of our satellite systems just because there's so many and they are moving at such a high speed. It wouldn't take much, like half a dozen pebbles in the right place, and you could wipe out a good chunk of satellite communication. So ESA is actually the one I was reading about this. They are actually starting to sort of track these showers and track these possibilities and look at how much of a threat that even natural objects can cause to space thing because, space junk and stuff like that, it's metal, it's fairly reflective. We can usually find it. Meteor showers, it's a bit of a different game. One, the particles are smaller, but second, some of them move really fast. So this is another thing they're starting to take into account with meteor showers is could they potentially pose a threat to, various spacecraft in orbit around Earth? Is this something we have to take into consideration and be aware of as yet another potential way you could lose a whole bunch of satellites?
It's interesting. I don't know if you'd heard in the news that the Chinese space station, a piece of space junk, impacted with the crew return capsule, and the Chinese astronauts are actually now stuck on the space station, and they're going to have to work out how difficult it is to, how are they going to bring them back? Are they going to have to launch? Can they repair the spacecraft? Are they going to have to launch a rescue ship? So try to imagine that's one piece of space junk. Try to imagine something like you described. And if you've ever seen it's a fictional movie, but the movie Gravity, where three space stations are destroyed, or I think two space stations and a space shuttle are destroyed by one random piece of space junk because these things are moving so fast, and
Oh
there's
yeah,
so much stuff up there. It'd be
I know,
so easy to wipe out a huge
oh,
chunk
I
of our
know. I mean, they're,
infrastructure.
they're starting to think about how can we start to capture some of this space junk we put up there. And the thing is,
Yeah.
with stuff we put in orbit, a lot of it will eventually sort of either float off into space or decay and burn up in the atmosphere. So, it's a problem that'll probably have it'll always be there, but these things will have, a limited lifespan. The catch is with meteor showers is they're always being renewed by the comets, and this isn't something where you can kind of track the orbits. This is going to be a little bit more problematic, right? So it's kind of a different kind of space junk problem, but still a problem. So
Well, yeah, but it cascades, right? So you get
yeah.
one errant meteor, which hits, a satellite, breaks it into a bunch of pieces, flying off in different directions, right? And they start to take out other stuff because it's crowded up there. And if you've got a lot of meteors, that could be repeated
Oh, I mean,
multiple
you
times.
could
So,
take out probably an entire Starlink train if you had, just the right set of circumstances with a couple of close together small meteorites.
yeah,
'Cause, I mean, even something the size of a pebble moving at that speed, if it hits it the right way, it's toast. So,
yeah, absolutely. And this is a problem we are going to. I mean, look, not the meteor problem, but the problem of space junk is one that we are going to have to address. And there's been a number of proposals on how to do it, but something is going to have to be done with it. Um, but I noticed that we're getting close on time, so I'm going to move us over to our last news item. Something we've been following here a fair bit at York Universe is our interstellar comet 3I Atlas, which has now passed behind the sun from our point of view. And it's not really ideally suited for viewing in southern Ontario. There is a virtual star party with some great telescopes, which give folks a chance to view it online. And I think we will post this link on our webpage for the show. But you can actually go there, and what happens is it's November 18th, so I guess that's tomorrow. Today, the 18th. Today is the 17th. It's
yeah.
tomorrow. Yes, a chance to witness. So there's some detailed telescope views of this comet. This is part of the virtual telescope project's U2 live stream. So there are a number of virtual telescopes in the world, and you can just go and look virtual telescopes, do a Google search. And what it usually is these are kind of smaller observatory grade telescopes. Some of them are free. Some of them are subscription models. And some of them are paid services. I use one myself. It's a paid service. If I need some images of something for my work, I can buy them processed. I can either buy them processed or process them up myself if I'm looking for various data extraction. But the nice thing about this is that the telescopes are widely distributed. So if you get bad weather in one location, you could have good weather in another location, and you can get a look at these. So again, it's absolutely worth checking this out. And this actually speaks to my mind to, again, something here that we take very seriously at the Allan Carswell Observatory, which is public outreach. This is a way of socializing the science and the beauty of astronomy. Um, even tonight with our broadcast, we've been looking at some live images. That is all part of our mission to communicate astronomy to the broader public. And I'm very excited when I see events such as this live telescope feed of this comet. But there's a lot of that out there, and it's something that if you're interested in astronomy, there's so many great tools and resources available online, and very often completely free. What do you think, Mary Helen?
I I just love watching these kind of things. I mean, I often often you don't hear about them or you don't have time, but I when I get a chance, whether it's sort of live landings when they tried to earlier this year, the one private company tried to land on the moon, or some of these live streams, they're cool. And even if you can't watch it at the time, they usually keep it posted so you can watch it later on. So.
Yeah. One of my favorite was the DART mission where they were impacting an asteroid, and in almost real time, not quite in real time, because there was some delay. But the asteroid Didymos in question was relatively close, and you could see the images coming in real time. My daughter and I watched it, and it was just amazing. It was almost you were biting your nails because you could see it was the spacecraft was self-directing towards the asteroid, and you could see it. Is it going on course? Is it centering? Oh, it's centering. Oh, look, it's getting closer, and there's the big asteroid moving aside, and there's the moon. We're getting close to the asteroid moon. It was incredible. But when I was young, you got, even during something as exciting as an Apollo moon landing, you might get 5 minutes of coverage in the news after the excitement of Apollo 11. And the way you found out about stuff was to grab a magazine like Astronomy or Sky and Telescope, and Sky and Telescope was for the serious amateur, and Astronomy, it was more for the public at large. But now all of those tools and so many more are available online, and it's just it's a great time to be interested in astronomy, and a great time to have kids who are interested in astronomy, because there's so many tools they can access so readily. And I know that at the end of this month we're going to be talking on our teletube about public outreach and with astronomy. So it is part of our mission, and but it's an exciting time to be interested in astronomy. So I guess we are getting near the end of our time. I'm going to close out with, time to close up our broadcast for this evening. Thank you for joining us. We've been listening to York Universe, the astronomy and astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Professor Mary Helen Armour and myself, Paul Mackin. This podcast and past episodes are available wherever podcasts are distributed. You can always connect with us on our Instagram with the handle at York Observatory, or on Facebook at Allan I Carswell Ob. Our website is yorku.ca/science/observatory. And we have a lot of interesting content there. And if you are so inclined, and we would certainly appreciate that, it's a great place to make a Canadian tax-deductible donation to our student-operated, not-for-profit observatory. Thanks for tuning in this evening. We wish you clear skies and good night.